Hey, this is section 6.8. How about 8.6? And we're looking at the cross product properties. Now, we've seen the definition, and given that the definition. So if I have my two vectors, x is maybe a x1, x2, x3, and a y, which is a y1, y2, y3 vector. Then x cross y is equal to the determinant of I j k. Now this is kind of weird because really we're saying these are vectors. So to me this is kind of a language idiom or something like that, because I can't actually truly do this this determinant of this, because these should all be scalars in here. But if I just treat the ijk like scalars and simply get the resulting determinant here, it works. So I'll call that an idiom. x2, x3 here, y1, y2, y3. So it's a vector. If I take x cross y to get some z, that is a vector. And so, it would have a particular magnitude and a particular direction to it. And so order is very important. And we know from determinants, right, if I swap these bottom two rows, so in other words, if I swap the order here, then we would get the negative. And so what's happening in terms of sort of the geometry is when you think of x cross y, we call it a right-hand system. And the way you kind of think of it is, now this is supposed to be a hand here. This is no Michael Nettleton kind of drawing here, but it'll do. There's a hand with a thumb sticking up, and the fingers are curling over. And the way you think of it is, if you stretched out your hand on the first vector, x, and you curled your fingers, so there's the curling, toward y, then and looked at where your thumb is pointing, either up or down or wherever, that is the direction of the cross product. So here we have x cross y. And so we call that a right-hand system because I'm using my right hand to do that. And similarly, if I did instead y cross x, then I would get my hand going this way to start with, but I would have to turn my thumb upside down to then get the right orientation to be able to curl my fingers this way. And so this is y cross x. Okay, so these are a right-handed system, and so we would determine the direction of our cross product vector using a right-hand system. And so various properties. They have property I is that I cross j. Okay, so that's the x-axis and y-axis standard unit vectors. You get k, and that's really kind of the picture I was showing there. And then if we take j cross k, we get I. And then what do we have now? K cross I. K cross y, we get j, and so this is a right-handed coordinate system. Okay, so our standard unit vectors work this way. Okay, so that's property 1, or I. They're using their Roman numerals. So actually, I'm going to use 1 because I think we need to get rid of Roman numerals. 2 is that if you take x cross x, you get 0, but it's a vector. You get a 0 vector. And you can look at that a couple of different ways. You know, one is, well, if I have just a single vector x and I ask for a vector orthogonal to it, well, that's a whole bunch of vectors, and so that interpretation, you know, looking at it that way, oh, I could find all kinds of vectors that were perpendicular to x. But in this case, the way we've defined this cross product in terms of a determinant like this up here, then, well, if we have 2 rows of a matrix are the same, we should get a 0 for a determinant, and so we'll take the 0 vector as our answer here. We've mentioned that y cross x is the negative of x cross y, and again, that just comes, if you think of the cross product as being this determinant up here, then swapping rows would certainly show that property. 4, it distributes over addition. So if we take x cross y plus z, then that's the same thing as x cross y plus x cross z. And of course, it's important, order matters, so I keep everything in that same order. 5, scalar multiplication. If I have t times, t times, well, if I can get the eraser to work there. There we go. T times x crossed with y, then I can pull that out and just get t times x cross y. Now they also mention this thing called the scalar triple product. So we have 3 vectors. So if, and I'll use their stuff here, they have that x is A1, B1, C1, and y is A2, B2, C2, and z is A3, B3, C3. Then they define the scalar triple product x dot y cross z as the determinant of A1, B1, C1, A2, B2, C2, A3, B3, C3, and then that is the same thing as x cross y dotted with z, so that's interesting. So this is just a formula. So they mention this, that the cross product is, so if I wanted x dot y cross z, I could do it with this determinant. And notice, since we have a dot product in there, we do a scalar out of the scalar triple product, as they call it. Let's see, 7. If we take x dot x cross y, we should get 0, right? Because x cross y is orthogonal to x. I mean, that's the way, in the way we developed it, that, that is how we made it. So this is of no surprise. And so same thing if I took y dotted with x cross y. 8, the magnitude of x cross y is equal to the square root of the magnitude of x squared, magnitude of y squared, minus x dot y squared. Okay. This can also be written another way. And so we need that, x and y are not equal to the 0 vector. And theta is angle between them. Then, just like we have two characterizations of the dot product, we've got a couple characterizations here of the cross product. So we have the 1 there in 8, but we can also do this as magnitudes, and this is the magnitude of x times the magnitude of y times the sine of theta. So the dot product magnitude was this same kind of thing, but with a cosine of theta. So this is with sine of theta. Now, and we're fine with not putting absolute values, because this is a magnitude here. We're fine with not putting absolute values on the sine of theta, because we'll always take theta, as far as the angle between the two vectors, we would probably take that as a positive angle, right? We wouldn't talk about a negative angle between them. I suppose there could be times when you would, in which case you would need an absolute value on there. Okay. And so those are all the properties, and we'll stop this video here.